340 meters of loose rock passing inside the ring of geostationary satellites. That is April 13th, 2029, and it has been on the calendar since 2004, when a team at Kitt Peak National Observatory found an asteroid the Egyptians would have named for Chaos, and then calculated a 2.7% chance that it would hit us. That number is gone now, ruled out for at least a century. This is the story of what replaced it, why the arithmetic behind the reassurance is solid, and why the reassurance is still missing a sentence. On the evening of April 13th, 2029, a point of light will rise over Europe and Africa and Western Asia, and it will not behave like a star. It will move fast enough to cross more than the width of a full moon in a single minute. It will brighten as it climbs, and something close to 2 billion people will be able to follow it with nothing but their eyes. That point of light is a rock about 340 meters across, near enough the height of the Eiffel Tower, and it is called Apophis, after the serpent the ancient Egyptians blamed for trying to swallow the sun. It will pass roughly 31,600 kilometers above the surface of the Earth, closer than the ring of geostationary satellites that carry our television and our weather data. Nothing this large has ever come this close in recorded history. And for more than 20 years, one question has followed that date around like a shadow. What happens when a loosely bound heap of rock passes that near to a planet? Does Earth's gravity pull it apart? Does it come down on us in pieces? That question has an answer. It is published, it is quantified, and it is not the answer most people have been given. It is also not the question that should keep you up. The fear is not foolish. It is built on a correct piece of physics, applied to a body that fits the description. Apophis is not a boulder. Radar shape modelling, led by Marina Brozović at NASA's Jet Propulsion Laboratory, published in 2018, shows a below-bed object, two masses joined at a narrow neck, and quite possibly a contact binary. Two separate bodies resting against each other, held there by almost nothing. Beneath that outline, the working model is a rubble pile. Not solid stone, but an aggregate of gravel and boulders and dust, bound together mainly by its own weak self-gravity. Richard Binzel and colleagues at MIT compared its bulk density against the density of the rock itself and worked out what the gap implies. An internal porosity anywhere from about 4% to 62%. Apophis may be more than half empty space, and it tumbles. It rolls once every 30.6 hours, while processing on a separate cycle of about 266 hours, so it never shows the same face on the same schedule twice. A porous, tumbling, loosely stacked heap of gravel, passing inside the satellite ring. If you set out to design an object to be torn apart by a planet, that is roughly what you would draw. So the question is fair. What follows is not opinion. It is arithmetic, and the arithmetic has already been done. For every body and every planet, there is a distance inside which the planet's tidal pull overcomes the body's own gravity, and the body comes apart. It is called the Roche limit, and where the line falls depends almost entirely on how dense the smaller object is. For a rubble pile of the density assumed for an asteroid of Apophis' type, that limit sits at about 3.4 times the radius of the Earth, measured from the planet's centre. Apophis will pass at just under 6. That figure comes from a 2023 paper in Monthly Notices of the Royal Astronomical Society, led by Yaeji Kim at Auburn University, with Joseph DeMartini and Derek Richardson at the University of Maryland. The perigee distance of Apophis during the encounter, they write, is outside the canonical Roche limit that induces catastrophic disruptions of unconsolidated material. Outside, not marginally, by a factor of roughly 1.8, and that is the generous version. A separate group, Ronald Louis Ballouz at the Johns Hopkins Applied Physics Laboratory, with co-authors from the Observatoire de la Côte d'Azur, MIT, and the University of Arizona, put the real boundary tighter still. Direct simulations, they write, show that only encounters closer than 3 planetary radii lead to global-scale disruption or mass shedding. 3. Apophis arrives at 6. The most detailed test of where that line sits came in 2020 from Zhang and Patrick Michel at the Laboratoire Lagrange in Nice. They simulated rubble piles on flyby after flyby, sweeping the approach distance from 1.1 to 2.5 Earth radii, and sorted the outcomes into 3 kinds. At 1.9 Earth radii, the body deforms. Its shape changes, its spin changes, and it loses nothing. At 1.6, in their words, marginal mass loss at the extremities of the progenitor. The first material comes off, from the ends, like crumbs. At 1.3, full breakup into smaller separate pieces. So the first flake of Apophis would come loose at under 1.9 Earth radii. It arrives 3 times farther out than that. This is not a close call. We know what it looks like when a body does cross that line, because we watched it happen. In 1992, a comet called Shoemaker-Levy 9 passed within 1.33 Jupiter radii of that planet's centre. That is well inside the line, and Jupiter's tides did exactly what the models say they do. The comet came apart into a chain of 21 separate fragments, strung out along its orbit like a string of pearls. 2 years later, those fragments struck Jupiter one after another and left dark bruises in the cloud tops, larger than the Earth. That is the image living behind the Apophis sphere. But look at where it happened. 1.33 planetary radii, not 5.96. To reproduce Shoemaker-Levy 9 at Earth, Apophis would have to arrive 4 times closer than it will, which would put it not near our satellites, but through the upper atmosphere. Zhang and Michel make one more point worth holding on to. Above the failure limit, they write, the rubble piles are impervious to the tidal effects and can preserve their original shapes and rotation states. Impervious is a strong word for a scientist, chosen deliberately. Tidal disruption is not a gradient. It is a threshold. You are inside it or you are not. Apophis is not. So the loud version of the story is wrong, which raises a better question. What does happen up there in the hour that rock spends inside our satellite ring? Something will happen. It will simply be small, fast, and almost impossible to see from here. Kim and her colleagues modelled the surface patch by patch, across 30 different orientations Apophis might present as it comes through. Their prediction: tidal resurfacing, limited to certain localized regions, beginning about half an hour before closest approach, and affecting around 1% of the entire surface area. 1%. On a body 340 meters across, that is a few tennis courts of gravel. The motion is centimetric, and only the top half meter or so of loose material takes part. The places most likely to shift are the steepest slopes, anything above 30 degrees, and, in every single one of their 30 runs, the narrow neck between the 2 lobes. Whatever else the encounter does, it pulls at the waist. Ballouz and his team modelled the whole body instead of the surface 54 times over, and found something nobody expected. The encounter, they write, can excite high-frequency shaking to magnitudes that reach levels of Apophis's self-gravity. For a few minutes, the asteroid shakes itself as hard as it holds itself together. The events begin about an hour before closest approach. Seismic waves spread across the surface at roughly 100 meters per second, slow enough that you could nearly outrun them. Strong shaking persists between a minute and a half and 15 minutes. and the background vibration of the whole object jumps by a factor of 10. And here is the honest deflation, in the author's own numbers. The physical displacement required to produce shaking that violent, at those frequencies, is less than 1/10 of a millimetre. Apophis will ring like a struck bell. The bell moves less than the width of a human hair. The one effect we will be able to measure from here is the spin. Across all 54 simulations, the roll period comes out between 18.6 and 40 hours, against 30.6 going in. Earth will reach out, grab a tumbling mountain, and add or subtract a few hours from its day. That is the whole event, not a shattering, a tremble and a nudge. Picture standing there, not watching from below, standing on it, on the neck between the two lobes, on the night it comes through. You would weigh almost nothing. The surface gravity is so faint that a careless step would put you into orbit, and you would come back down minutes later like a leaf. The ground under your boots is not ground. It is a heap of gravel and dust and boulders that has been sitting undisturbed in places for hundreds of thousands of years, dark, dry, stacked at whatever angle it happened to settle into. Then the Earth arrives. It would not be a rush. It would be a slow filling of the sky. Over hours the blue disk would grow until it took up more of your view than anything has any right to. Close enough to pick out weather systems, coastlines, the Terminator sliding across the ocean. Half an hour before the closest point, the ground would begin to move. Not violently. Individual grains on the steepest slope sliding a few centimetres downhill and stopping. Dust lifting a fraction and settling again. The whole surface humming at a scale you would feel in your bones more than see with your eyes. Then the Earth would shrink, the ringing would fade, and the asteroid would go back to being what it was. A tumbling heap of rock, with a day a few hours longer or shorter than before. Nothing breaks. Nothing falls off. Which brings us to the part of the fear that survives the arithmetic, because even if Apophis does not shatter, something does come loose out there. The question is where it goes. That question has been asked properly, in print, and the answer took 200 years of simulated time. In 2024, a team led by Gabriel Valvano at São Paulo State University in Brazil, with Rafael Sfair at Tübingen and Gabriel Borderes-Motta at the Universidade Carlos III de Madrid, published a paper in monthly notices of the Royal Astronomical Society, whose title is simply the question itself. May a meteor activity happen on Earth after the 2029 closest approach? They set it up deliberately generously. Rather than model dust shaken off the surface, which remember may not lift at all, they assumed something more extreme. A disk of 15,000 particles, already in orbit around Apophis before the encounter, a kilometre wide. Then they let Earth's gravity work on it. Roughly 80% of that disk gets stripped away. About 12,000 particles pulled free of Apophis entirely, at speeds slower than a walking pace, then tracked forward for 200 years, under the gravity of the Sun, the Earth, the Moon, Venus, Mars, and Jupiter. The conclusion is one sentence. It is unlikely, they write, for a meteor activity to occur from any particle that escaped from Apophis's gravitational field over the 200 years following the close approach. Not unlikely in the sense of rare, unlikely in the sense that it did not happen once in the simulation. And the reason is a detail no amount of drama can talk around. The particle orbits do eventually cross Earth's orbit, and their closest approach distance drops all the way into collision range. But, in the author's words, there is no collision, because the particles and the Earth were never in the same angular region of the orbit at the same time. Where the two orbits overlap, the stream sits hundreds of Earth radii above or below our orbital plane. The stream trails Apophyses closely for about 73 years. At 87 years, an Earth encounter kicks the dispersion open, and by roughly a century it wraps the full circle of the orbit. Only then does anything get near us, and it is not us. From about the year 2117 onward, a small number of those orbits pass inside the Earth-Moon distance, and the Moon might eventually catch a few. The authors quantify it themselves. 1.9% of the particles and the likelihood of significant meteoroid activity is, in their assessment, low. So there it is. The rock will not break. The pieces, if there were pieces, would not reach us, and the Moon would have to wait 90 years. The file is closed, except it is not. Since the middle of 2021, nobody on Earth has been able to see Apophis. It is not hiding. It is in the daytime sky, lost in the glare of the sun. Its angular separation from the sun does not open up to 60 degrees, the point at which serious observation becomes possible, until the 22nd of February, 2027. And when it emerges, it will be around magnitude 21, faint enough to require real time on a large telescope. More than 6 years. Blind. Now hold that against the reassurance. Every statement you have ever read about April 13th, 2029, the 31,600 kilometers, the impact ruled out for a century, the naked eye spectacle, traces back to a trajectory solution built on observations that end in early 2021, when the Goldstone antennas in California and the Green Bank telescope in West Virginia closed the case by radar. That solution is excellent. It is also being propagated forward on paper, across more than 6 years, in which nobody has been able to check it. For almost all of that time, the assumption behind the propagation is trivially safe. Nothing out there is going to touch it. Asteroids drift through empty space. Almost. In 2024, Paul Wiegert, an astronomer at the University of Western Ontario, published a paper in the Planetary Science Journal that asked a question nobody had bothered to formalize. Every trajectory ever computed for Apophis assumes that nothing hits it, but small asteroids strike bodies across the inner solar system constantly and without warning. That is what a shooting star is. Apophis has been sitting out there, unwatched, for 6 years. What if something clipped it? So he ran the numbers. Thousands of scenarios, each applying a velocity change to Apophis from a random direction, at a random moment between 2021 and 2029, then measuring what that did to the approach. 2 thresholds came out of it, a velocity change of about 0.3 of a millimeter per second, a nudge so small it barely qualifies as a nudge, is enough to shift Apophis relative to its keyholes. The narrow windows in space that, if it threaded one, would set up an impact on a later pass. The probability, less than 1 in a million, and a velocity change of 5 centimeters per second or more, which would take an impactor around 3 meters across, is enough to deflect Apophis into an actual Earth impact in 2029. The probability, less than 1 in a billion. Let me be precise about what those numbers mean, because this is where the story usually gets broken. 1 in a billion is not a warning. The threshold the field uses for taking an impact risk seriously is 1 in a million, and this sits 1,000 times below it. Wiegert himself calls impulses of that size extremely rare. Nobody is worried, and nobody should be. But it is not 0, and of every quantity in the entire Apophis file, the size, the density, the spin, the shape, the perigee, the Roche limit, that is the only one currently unmeasured, rather than merely small. Everything else has been observed. That one was calculated in the absence of observation. Wiegert also tells us when it ends. An impending impact, he writes, would be signalled clearly in most cases by deviations of tens of arc seconds from the predicted position in 2027. And most of the risk could be retired by a single observation. One night, one telescope. February of next year. The keyhole question is harder. A deflection into a keyhole might move it by only a few tenths of an arcsecond, which is not something a single night of data will settle. So this is what is actually true about the flyby. Earth's gravity will not tear Apophis apart. Nothing that comes off it reaches us this century or the next. And the one genuine unknown is not about the rock at all. It is about a 6-year gap in our attention. The gap is closing, and not by waiting. The European Space Agency committed to a mission called RAMSES, the Rapid Apophis Mission for Space Safety, at its Ministerial Council in November of 2025. The construction contract, worth €81.2 million, was signed with OHB Italia on the 10th of February this year, and in May, in Berlin, ESA and the Japan Aerospace Exploration Agency signed the agreements that will put it on a Japanese H-3 rocket in the spring of 2028. RAMSES arrives before the flyby. That is the entire point of it. For the first time, we will have instruments alongside an asteroid going into a planetary encounter, measuring its shape, its spin, its interior, and then measuring the same things afterward. NASA's OSIRIS-APEX, the repurposed spacecraft that brought a sample of asteroid Bennu home in 2023, is already on its way. Led by Danny Della Giustina at the University of Arizona, it will spend around 18 months in orbit at Apophis afterward, mapping what Earth's gravity did to it. Ballouz and his colleagues describe what that gives us in one phrase: our first direct probe of an asteroid's interior. Think about what that means. We do not have to drill into it, or hit it, or land on it. We let a planet squeeze it and watch the response. Earth is running the experiment whether we show up or not, which is the reversal at the center of all this. We spent 20 years asking whether Apophis would break apart over our heads, and the answer was always sitting in the arithmetic, 3 times out, unambiguous. The thing we should have been asking is quieter and much more human. That we stopped being able to see it. That we filled the gap with a calculation. And that the only number in the file, which is not 0, describes what might have happened while we were not watching. It resolves in February. A single night, a large telescope, a faint smear of light at magnitude 21, where the arithmetic says it should be. Almost certainly it will be exactly where we left it. Almost is the word doing the work. Thanks for watching, and I'll see you in the next one.